Welcome! Today, we will dive into LeetCode problem number 1152, Analyze User Website Visit Pattern. The goal of this problem is to identify the most frequent 3 website visit sequence for users based on their browsing data. Let's explore the problem, understand its requirements, and work through a solution step by step. Let's get started. In this problem, we are tasked with analyzing patterns in website visits by different users. Specifically, we want to find the most visited sequence of 3 websites, known as a 3 sequence, that users access in the same order. The input consists of 3 arrays: username, timestamp, and website. Each array is of the same length, and then ith index in all 3 arrays represents one website visit. The username array tells us which user visited a website, the timestamp array specifies the exact time of the visit, and the website array identifies the site that was visited. The output should be a list of 3 strings representing the most frequently visited 3 sequence. If there are multiple 3 sequences with the same frequency, we return the lexicographically smallest one to ensure consistency in the result. To better understand the problem, let's look at the first example. Here, we are given the username, timestamp, and website arrays. For instance, user Joe visits 3 websites in the sequence home, about, career, while James visits 4 websites, but no 3 sequence repeats. Finally, Mary visits the same 3 websites as Joe in the same order. The pattern home, about, career occurs twice, which is more frequent than any other pattern. Since it has the highest frequency, it is the result. This example helps illustrate how we track and compare patterns across different users. In the second example, we have 2 users, U1 and U2, with their respective website visit sequences. For U1, the 3 sequence of B, A is observed, while for U2, the sequence of B, C is formed. Both patterns occur only once, but since we need to return the lexicographically smallest sequence in case of a tie, the result is a B, A. This example highlights how ties are resolved by comparing the patterns alphabetically, ensuring that the solution remains consistent and deterministic. Now let's consider the problem constraints and some key edge cases. First, the length of the input arrays will always be at least 3 and at most 50. The timestamps are strictly increasing, ensuring that the order of visits is unambiguous. Both usernames and website names consist of lowercase English letters. Additionally, there is always at least one valid 3 sequence. Important edge cases include handling single users with multiple patterns, ensuring proper lexicographical comparison when frequencies tie, and correctly aggregating patterns across multiple users. These constraints and considerations guide us in implementing an accurate and efficient solution. To solve problem number 1152, which involves analyzing the most frequent sequence of 3 websites visited by users in order, we considered several approaches. One of these is the brute force method. The intuition behind this approach is straightforward: for every user, generate all possible combinations of 3 website sequences, count the frequency of each sequence across all users, and return the most frequent one. In cases where multiple sequences have the same frequency, the lexicographically smaller one is chosen. The steps include grouping input data by user, sorting each user's website visits by timestamp, generating all possible 3 sequence combinations for each user, and then using a dictionary to count the frequency of these sequences globally. Finally, we identify the most frequent sequence. However, the computational cost is significant. Sorting the visits for each user takes time proportional to the number of users multiplied by the average number of visits per user, while generating combinations and counting sequences adds a cubic growth factor for users with many visits. Overall, this approach has a complexity of v log v plus v cubed, which can become unmanageable for larger inputs due to the cubic growth in sequence generation. An optimized approach addresses the inefficiencies of the brute force method by reducing redundant computations. Here, we focus on limiting sequence generation to unique users and use Python's collections counter for efficient frequency counting. The steps are similar to the brute force method, starting with grouping visits by user and sorting them by timestamp. However, instead of generating all possible sequences, we use a set to store only unique 3 sequences per user. These unique sequences are then added to a global counter, which efficiently tallies their frequencies. To find the most frequent sequence, we use the counter's most_common method. While the sorting step remains the same, the use of a set eliminates redundant sequences, and the frequency counting is faster due to the optimized data structure. The complexity remains O, U asterisk V log V plus U times V cubed, but the reduced overhead makes this approach more efficient. We also considered other alternatives, such as sliding windows and prefix trees. Sliding windows could theoretically generate sequences, but they're inefficient for counting sequences across users. Prefix trees, while compact, introduce additional complexity during insertion and traversal, which is unnecessary for this problem. The optimized approach was chosen because it balances simplicity and efficiency. Sorting visits is a necessary step to preserve the order of website sequences, but generating unique sequences per user avoids redundant computations, simplifying the overall process. Additionally, Python's collections counter makes frequency counting both fast and straightforward, allowing us to easily identify the most common sequence. Key insights during this process include the importance of grouping data by user early, as this minimizes unnecessary operations later. Lexicographical tiebreaking, which might seem complicated at first, is naturally handled by sorting sequences beforehand. Another critical observation was that handling unique sequences per user prevents overcounting patterns shared by multiple users. While the brute force approach is intuitive, its computational expense makes it unsuitable for larger datasets. Sliding window and tree-based solutions, on the other hand, add unnecessary complexity. The optimized approach is clear, efficient, and maintainable, making it the best choice for solving this problem. The final complexity of the chosen approach is approximately O, U asterisk, V log V plus V cubed, where U represents the number of unique users and V is the average number of visits per user. While the cubic term in V may seem high, the problem constraints ensure that the number of visits per user is limited, making this complexity feasible in practice. By reducing redundant computations and leveraging efficient data structures, the approach remains practical for the input sizes typically encountered in this problem. To tackle the problem of analyzing user website visit patterns, we start by organizing the input data effectively. The input consists of 3 lists: username, timestamp, and website, all of equal length. Our first step is to group the website visits by users while ensuring that these visits are sorted in chronological order. To do this, we combine the 3 lists into a single collection of tuples, where each tuple contains the username, timestamp, and website. Sorting these tuples first by username and then by timestamp ensures that the visits for each user are correctly ordered. Once sorted, we use a dictionary to map each unique user to their respective list of websites visited. For example, if user 1 visited Site 1, Site 2, and Site 3, and user 2 visited Site 4, Site 2, and Site 3, our dictionary structure would reflect this grouping. This step sets the foundation for efficiently analyzing patterns in subsequent stages. Now that we have grouped and sorted the data by user, the next step is to generate all possible 3 website sequences for each user. Using the sliding window technique, we can efficiently extract these sequences from the list of websites visited by each user. For instance, if a user visited the sequence Site 1, Site 2, Site 3, Site 4, we can generate the 3 sequences Site 1, Site 2, Site 3, and Site 2, Site 3, Site 4. This method ensures that we capture all consecutive 3 website combinations without repeatedly iterating over the data. Once we have the sequences for each user, we need to count their occurrences across all users. To do this, we use a dictionary to store the frequency of each unique sequence. Importantly, we avoid double-counting sequences that appear multiple times for the same user by using a set to track unique patterns for each user before updating the global counts. A few key insights make this algorithm both efficient and accurate. First, sorting the data by timestamp ensures that the websites visited by each user are in the correct chronological order, which is critical for analyzing patterns. The sliding window technique is particularly useful here, as it allows us to extract 3 sequences efficiently without redundant computations. Additionally, tracking sequences with a set at the user level ensures that duplicate patterns from the same user are not overcounted, preserving the integrity of our frequency analysis. Finally, to handle ties in sequence frequency, we rely on the natural lexicographical order of tuples. This simplifies the process of determining the smallest sequence without requiring additional sorting or processing. The algorithm also leverages well-suited data structures, dictionaries for grouping website visits by user and tracking global sequence counts, and sets to ensure user-level uniqueness of sequences. The final step involves using the dictionary of global counts to determine the most frequent 3 sequence across all users. This dictionary efficiently tracks the frequency of each sequence, making it straightforward to iterate through and find the sequence with the highest count. If multiple sequences have the same highest frequency, we break the tie by selecting the lexicographically smallest sequence. As for the algorithm's complexity, sorting the data by timestamp takes n log n, where n is the total number of records. Generating sequences for each user takes m*k, where m is the number of users and k is the average number of websites visited per user. Counting the sequences and identifying the most frequent one takes p, where p is the number of unique sequences. Combining these, the overall time complexity of the algorithm is n log n plus m*k plus p, ensuring it is efficient for large datasets. The solution begins by combining the input list's username, timestamp, and website into a single list of tuples. Each tuple contains the timestamp, username, and website, and the list is then sorted by timestamp to ensure chronological order of visits. This ensures that the sequence of visits for each user is accurate. Next, a dictionary user_visits is created to group website visits by each individual user. The keys in this dictionary are usernames, and the values are lists of websites visited by that user in chronological order. The third step involves generating all unique 3 sequence patterns of website visits for each user. This is done using the combinations function from the itertools module, which produces all possible combinations of 3 websites from the user's visit list. A set is used to ensure that duplicate patterns for the same user are not counted multiple times. For each unique pattern, a counter object is used to keep track of the frequency of each 3 sequence pattern across all users. Finally, the most visited pattern is determined by finding the pattern with the highest frequency in the counter object. In the event of a tie, i.e., multiple patterns have the same maximum frequency, the sorted function ensures that the lexicographically smallest pattern is chosen. The result is converted to a list and returned as the output. Here, we begin by defining the main method to solve the problem. The goal is to determine the most visited 3 sequence pattern of websites by users. First, we create a helper class called visit to encapsulate the details of a visit, including the timestamp, username, and website. Then, we initialize a list of visit objects and populate it by combining the 3 input arrays, username, timestamp, and website. Once the visits are populated, we sort them by the timestamp using a comparator. This ensures that the visits are chronologically ordered for accurate analysis. Next, we group the website visits by each user. Using a hash map, we map each username to a list of websites they visited. This forms the foundation for tracking user-specific browsing patterns. After that, we begin to analyze the 3 sequence patterns. For each user, we generate all possible combinations of 3 websites they visited, ensuring that the sequences maintain the chronological order. To avoid duplicates, we store these sequences in a set for each user. After generating the 3 sequence patterns for a user, we update the global count of patterns across all users. A hash map is used to store each unique pattern as a key and its frequency as the value. For every pattern generated, we increase its count in this map. With all patterns and their respective counts recorded, the next task is to determine the most frequent pattern. To do this, we iterate through the pattern count map. For each entry, we check if its frequency is greater than the current maximum frequency. If it is, we update our most visited list to this pattern and set the maximum frequency accordingly. If 2 patterns have the same frequency, we compare them lexicographically and select the smaller one. This ensures that in the case of ties, we return the lexicographically smallest pattern. By the end of this step, we have the most visited 3 sequence pattern ready to return. Finally, we define a helper class to structure the details of each visit, which is shown next. The visit class is a simple helper class designed to encapsulate the details of each visit. It contains 3 fields: timestamp, username, and website. These fields represent when the visit occurred, the user who made the visit, and the website visited, respectively. The constructor initializes these fields, making it easy to create visit objects from the input data. This class is critical for organizing and sorting the data in a structured way, ensuring that the main logic remains clean and efficient. By combining these fields into a single object, we simplify the process of handling and processing each visit throughout our solution. To solve this problem, we start by organizing the data. First, we combine the inputs username, timestamp, and website into a single list of tuples, where each tuple represents a visit and includes the timestamp, username, and website. Then, we sort this list by timestamp to ensure the visits are ordered chronologically. This gives us a structured view of the data as 1 U1 2 U1 B 3 U1 C 4 U2 5 U2 B 6 U2 A. After sorting, we group these visits by user. Each user's visits are represented as a list of websites they visited in order. For example, user U1 visited websites A, B, C, and user U2 visited A, B, A. This grouping helps us analyze the browsing patterns for each user individually. Now that we have grouped the visits by user, the next step is to analyze their browsing sequences. Specifically, we generate all unique 3 website sequences, or 3 sequences, for each user. For user U1, the sequence of visits produces the pattern A, B, C. Similarly, for user U2, the visits produce the pattern A, B, A. We keep track of how many times each 3 sequence occurs across all users using a counter. In this case, both patterns A, B, C, and A, B, A occur once, so the counter reflects counter A, B, C1, A, B, A1. Finally, to determine the most frequent pattern, we identify the 3 sequence with the highest count. If there is a tie, we select the lexicographically smallest pattern. Here, the output is A, B, C, because it is the smallest pattern in lexicographical order. In this example, the input data is slightly different, so we repeat the same steps. First, we combine the input into a list of tuples and sort by timestamp, resulting in 1 U1 2 U1 B 3 U1 4 U2 B 5 U2 6 U2 B. Then, we group the visits by user. User U1 has the sequence of websites A, B, A, while user U2 has B, A, B. This grouping gives us the foundation to analyze each user's browsing patterns independently. Next, we start generating the unique 3 sequences for user U1. The only pattern we can form from their sequence is A, B, A. For user U2, we generate the unique 3 sequence B, A, B based on their browsing history. Now, we count how many times each pattern occurs across all users. The counter shows counter A, B, A1, B, A, B1. Since both patterns occur only once, we apply the tie-breaking rule, choose the lexicographically smallest pattern. Between A, B, A, and B, A, B, the smaller pattern is A, B, A. Therefore, the final output for this example is A, B, A. In this case, we have only one user, U1, who visited 4 websites in sequence, A, B, C, D. First, we combine the input into a list of tuples and sort by timestamp, resulting in 1 U1 2 U1 B 3 U1 C 4 U1 D. Then, we group the visits by user, which gives us U1 A, B, C, D. Next, we generate all possible 3 sequences from the sequence of websites visited by user U1. The patterns we can form are A, B, C, D, A, C, D, and A, B, D. Each of these patterns occurs exactly once, so the counter shows counter A, B, C1, B, C, D1, A, C, D1, A, B, D1. Since all the patterns occur only once, the tie-breaking rule determines the result. We select the lexicographically smallest pattern from the set of 3 sequences. Comparing A, B, C, D, A, C, D, and A, B, D, the smallest pattern is A, B, C. Thus, the final output for this example is A, B, C. Here, we begin by analyzing the time complexity of the solution. The first major step is sorting the visits. The zip function combines the timestamp, username, and website into a list of tuples, which requires O, N, time for N website visits. Once combined, the sorted function organizes these tuples by timestamp, and since sorting takes O n log n time, step 1 contributes O n log n to the overall complexity. Moving to step 2, we group the website visits by user using a default int. This involves iterating through the sorted list and appending each visit to the corresponding user. As this iteration takes O n time, step 2 adds O n to the total complexity. Together, these initial steps efficiently prepare the data for further analysis. Next, we analyze steps 3 and 4, which account for the most computationally intensive parts of the solution. In step 3, we generate all unique 3 sequences for each user using the combinations function. If a user has visited m websites, generating these 3 sequences takes O m cubed time, as the number of combinations scales with O m choose 3. For k users and n total visits, this process is bounded by O n cubed, in the worst case, assuming all visits belong to one user. Incrementing the count for each sequence is an O1 operation per sequence. Then, in step 4, we identify the most frequent pattern by iterating through the pattern underscore count keys, which takes O p time for p distinct patterns. Sorting these patterns lexicographically adds O p log p, where p can reach O n cubed in the worst case. As a result, step 4 contributes O n cubed log n to the time complexity, highlighting the importance of optimizing these steps. Now we can combine the contributions of all steps to determine the overall time complexity. Sorting the visits in step 1 requires O n log n, grouping them in step 2 adds O n, counting patterns in step 3 contributes O n cubed, and lexicographically sorting patterns in step 4 adds O n cubed log n. Since steps 3 and 4 dominate, the overall time complexity in the worst case is O n cubed log n. Shifting to space complexity, we begin with step 1, where the visits list stores n tuples, each consisting of a timestamp, username, and website. This requires O n space. In step 2, the user underscore visits dictionary holds a list of websites for each user. If all visits are from distinct users, this also takes O n space. These initial steps ensure efficient storage without excessive memory usage. In step 3, we analyze the space required for counting patterns. The pattern underscore count dictionary tracks the frequency of each unique 3 sequence. If all sequences are distinct, there could be O n cubed unique patterns in the worst case. Each pattern is stored as a tuple of 3 websites, and assuming each website string takes O1 space, the total space required for pattern underscore count becomes O n cubed. When sorting patterns in step 4, no additional space is needed beyond what is already used by the pattern underscore count dictionary. Thus, the space complexity is dominated by the storage of patterns, resulting in an overall space complexity of O n cubed in the worst case. This aligns with our earlier observation that counting and storing patterns is the most resource-intensive part of the solution. To better understand the efficiency of the solution, let's compare it to a naive approach. A brute force method would involve examining all possible 3 sequences across all visits without considering user groupings. This would result in O n to the power of 4 time complexity, as generating O n cubed 3 sequences would require O n iterations for each. The optimized solution avoids this inefficiency by grouping visits by user, reducing redundant computations and bringing the time complexity down to O n cubed log n. Additionally, analyzing best, average, and worst cases provides further clarity. In the best case, with few users or websites, the number of 3 sequences decreases significantly, and time complexity approaches O n log n, dominated by sorting. In a balanced average case, the complexity is O n cubed log n, while in the worst case, where all visits belong to one user and sequences are unique, the time complexity remains O n cubed log n. Finally, we can confirm the derived time complexity of O n cubed log n. This is primarily due to 2 computationally expensive steps, generating all 3 sequences, which takes O n cubed, and sorting these sequences lexicographically, which adds O n cubed log n. These terms dominate the less intensive operations like sorting visits or grouping by user, so the overall time complexity is solidly O n cubed log n. This proof reinforces that the solution is optimized for the problem's constraints, striking a balance between accuracy and efficiency. When working on this problem, there are several common mistakes to watch out for. First, failing to sort website visits by timestamp can disrupt the chronological order of sequences, which is crucial. A valid sequence must reflect the actual order in which a user visited the websites, so skipping this step will result in incorrect outputs. Next, improperly grouping data by users can lead to mixing visits from different users. This creates sequences that don't represent real user behavior, making your results invalid. Another mistake is inefficiently generating and counting sequences. Without careful optimization, this process can become computationally expensive. For example, trying to create all possible 3 website combinations using brute force will quickly become impractical as the dataset grows. Lastly, edge cases are easy to overlook but critical to handle. For instance, users with fewer than 3 website visits should be skipped to avoid runtime errors or incorrect results. Being mindful of these pitfalls will help you avoid common errors and improve your solution's reliability. Overcomplicating your data structures is another area where mistakes can arise. It might seem tempting to use nested dictionaries or custom classes, but these can make your code harder to debug and maintain. Instead, a simple dictionary with tuples as keys is often sufficient for counting sequences efficiently. Now, from an interview perspective, there are a few key points to focus on. First, hash maps are your best friend here. Using them effectively to group and count sequences demonstrates your ability to choose appropriate data structures for the task. Additionally, discussing edge cases is a great way to show your thoroughness. For example, you can explain how you handle users with fewer than 3 website visits or situations where multiple sequences have the same frequency. Scalability is another concern you'll want to address. Be ready to talk about the time and space complexity of your solution, especially as the number of users or website visits scales up to tens of thousands. Finally, it's important to clearly articulate the reasoning behind your design choices, such as why you use dictionaries and tuples, and how those choices improve performance. This depth of understanding will leave a strong impression on your interviewer. This problem also shares similarities with several related LeetCode problems, which can help you build transferable skills. For example, in problem 49, group anagrams, you also use hash maps to group data based on shared characteristics, this time, anagrams. Similarly, in problem 763, partition labels, the task involves careful grouping of data according to unique constraints, which parallels the need to group website visits by user in this problem. Problem 347, top K frequent elements, focuses on identifying the most frequent items efficiently, a skill that applies directly to counting and ranking sequences here. Lastly, problem 895, maximum frequency stack, provides another example of leveraging hash maps to track both frequency and order, concepts that are also central to solving this problem effectively. Exploring these related problems can deepen your understanding of how to apply hash maps and grouping techniques across a variety of scenarios. Now, let's consider some alternative approaches and their trade-offs. A brute force approach is the simplest to implement. It involves generating all possible sequences for every user and counting their frequencies. However, this method is highly inefficient, with a cubic time complexity, making it impractical for large inputs. On the other hand, an optimized approach uses hash maps to group and count sequences more efficiently. By sorting data by user and timestamp, then generating sequences directly, you can significantly reduce runtime to linear or near-linear complexity. The trade-off here is a slight increase in code complexity, but the performance gains are well worth it. Another option is to use custom sorting methods. Instead of sorting by timestamp outright, you could pre-process the data into a more structured form, such as tuples containing the user, timestamp, and website. This pre-processing step may introduce additional overhead but can simplify the sequence generation process later on. Each approach has its strengths and weaknesses, so choosing the right one depends on the problem constraints and input size you're dealing with. Thank you for joining me on this walkthrough of LeetCode problem number 1152. We explored how to analyze user website patterns and identify the most frequent 3 website sequences using hash maps and sorting. Remember that pre-processing data is often key to solving complex problems like this efficiently. If you found this helpful, please like and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!